Hello and welcome to the Daily Space for September 3rd, 2018. My name is Dr. Pamela Gay and I am coming to you from Edwardsville, Illinois. After 2 weeks of escaping over to Europe and remote transmitting with some help from folks here in Edwardsville covering for me quite often, I worked to bring you all I could from the International Astronomical Union meeting. Well, now that I'm home, I'm going to be working to bring you a little bit more newsy kind of news. So, I'm looking at the messages I'm getting on delay. I'm sorry that I started a couple of moments late today. It turned out that my technology was set up for the hardware I had with me in Austria and not for the hardware I had here on my desk. Hopefully, from here on out, everything will be going smoothly. Now, to try and bring you today's top stories. Our first story for the day comes with interrupting messages, it looks like. I apologize that our chat is scaled quite oddly in most cases. I will be working to get that fixed. So this image that you're looking at is one that was taken with the ALMA telescope down in Chile. This is the Atacama Large Millimeter Array. This image is something that, thank you Fenrig, thank you so much. This image is one that goes beyond anything that we thought we would be able to do. Now, it doesn't look like all that much here. We have in the center this blob, and then we have these amazing radio outflows going in both directions. Now, what makes this so amazing is this is the youngest protostar ever to be seen to have disks and jets. So this particular object is located in the constellation Perseus, and it's 770 light years away, and it has the ever so romantic name of HH211. Now, with this object, what makes it so amazing is it's only 15 AU across. So when you look at the disk here in the center, this disk is significantly smaller than any of the disks we've ever been able to reveal before. And with the protostar only being 10,000 years old, this little tiny still forming disk around this extraordinarily young, not yet formed star puts new constraints on how stars form. We now know that they start to form disks even earlier than we had previously known. We can now identify the jets coming off of these young systems, and seeing these levels of detail means that from now on, the theorists have one more constraint to put on their models. Now, this doesn't rule out many of our current theories, but it does say this is when it starts. Make sure your models show the stars starting by 10,000 years after their formation. This is kind of fabulous. So I see Hanny saying that they didn't know that protoplanetary disks have jets. Yes, it turns out that pretty much any object with a disk of material where some of that material is inflowing onto the central object will end up having a strong magnetic field and jets of material coming out perpendicular to that disk. Whether we're looking at young stars, T Tauri, Wolf-Rayet stars, or whether we're looking at the accretion disks around high mass objects like neutron stars, or even the accretion disks around supermassive black holes. In all of these different systems, we have identical physics, and what's really cool is we get to see exactly how this kind of a physical configuration works at a variety of different masses and energy levels. Now, moving beyond planet star formation, we now instead look at what happens when things are in the process of dying. In these two images, we have the large Magellanic Cloud here on the left and the small Magellanic Cloud here on the right. Now, if these don't look familiar to you, that's because these images are taken using cosmic rays. In these images, we see the excitation caused by cosmic rays interacting with the gas and dust within these two dwarf galaxies that are orbiting our own Milky Way. We're seeing these objects, which are about 200,000 light years away. And to help you get your bearings, if you're familiar with the 30 Doradus star cluster, this right here is the 30 Doradus system. Now, because we're looking at these things using excited gas that's excited by cosmic rays, what we can really hone in on is where is the star formation taking place and where exactly have there been supernovas. Where you see the brightest points, these are the supernova remnants, the youngest stars, and of course star forming clusters. This is an amazing system, and when we look at it, the colors that we're looking at don't actually make any sense to the human eyeball. So the colors in these systems are actually 123 megahertz, 181 megahertz, 227 megahertz, and these different colors, which are not visible to the human eye, have been recolored to RGB. So essentially we took three actual colors our eyes can't see, recomposed them using, well, colors our computer monitors can display to allow us to see something beyond our eyes' ability. Now, this is early observations that were taken with the Murchison Wide Field Array, working with the International Center for Radio Astronomy Research, ICAR. This is a joint venture between Curtin University and the University of Western Australia. So here we have an image of the sky as taken from the outback of Australia. Now, if you wanted to look for these systems yourself, you need to go outside in the southern hemisphere. The large and small Magellanic Clouds can be found near the Milky Way. This is a panoramic image. You can't actually see all of this at once. So here we have the small and here we have the large Magellanic Cloud. So this particular set of images of the large and small Magellanic Clouds give us a hint of what we'll be able to see once the square kilometer array becomes online. This is just an introductory image. These images are at lower sensitivities than what the square kilometer array will be able to do. So now we're reaching the point where the science that we can do actually maps out to, well, tracing out gas excited by cosmic rays, allowing us to see the secondary glow caused by elusive particles that otherwise we just can't quite focus on. So this is cool science, this is introductory science, and it's kind of awesome. Now, as I said, a lot of these bright points in these particular clouds are created by the interaction of cosmic rays generated by supernova and the surrounding medium. Now, it turns out this isn't our only story involving supernova today. This particular image, well, it's not actually an image. This is an artist's rendering of exactly what the surroundings of a red supergiant star might look like. When red supergiant stars explode, they explode as a regular everyday supernova that we cannot use to measure distances. And astronomers looking at supernova like this have been trying to find the initial flash that indicates a supernova is about to take place, and then measure the upswing as the shocked material begins to illuminate the surroundings of the star. Now, unfortunately, they haven't been able to identify that initial flash using red supergiant supernova. They've also found that the way the star's light curve was shaped was unlike anything that they had predicted. Well, after following up with supernova after supernova and trying to model the end days of the star, what astronomers have concluded is this particular kind of supernova occurs in a concentrated environment. The red supergiant, in its final days, gives off the outer parts of its atmosphere. This material essentially encapsulates what remains of the star. When the supernova takes off, it radically illuminates the surrounding material, creating a sudden uptick and flattening off of the supernova light curve that is unlike what you get if you run a simulation that doesn't include the surrounding material. So here, what we believe is happening is that final exhalation of the star's atmosphere surrounds it in material that causes this to be a slightly reddened supernova. It rises in brightness faster, and unfortunately we can't observe this level of detail. So the only reason we're pretty sure this is true is because all the computer models that we build that work off of this idea of a surrounding thickness of material are able to reproduce what is observed, but models that don't include this material don't match what is observed. So this is one of those cases where our observations don't yet allow us to observe the details, but what we can observe allows us to build computer models based on theories that allow us to test, does the model match what we see or does it not? Based on whether the models match, we are able to, in a secondary kind of way, test the reality of our theories. I don't know if we'll ever be able to see these things in the kind of detail necessary to see the inner details. This is in part a problem of predicting exactly what star is going to go supernova when and knowing which to look at in detail. But it's an interesting start to being able to continue making interesting observations. Now, coming a bit closer to home, we have new updates on the Cassini, famous hexagon. In this animation, we can see the hexagon corrected for planetary rotation. This means that everything that you're seeing in this animation is related to the storms moving relative to the planet, not due to the planet's actual rotation. This allows us to see that this is some sort of a standing wave, and that within the hexagon you can still have amazing individual storms. Here we see this white storm down in the lower right. That particular storm itself is far larger than we might generally imagine. In fact, that particular storm, as was observed back in 2012, that particular storm is 3,500 kilometers across. So basically, it's bigger than the continental United States by a lot. If you took the widest section of the North American continent, going from Nova Scotia over on the east down to the outer parts of Alaska, it's still bigger than that. So this gives you a sense of scale for Saturn itself. Now, new observations, or new analysis of old observations rather, taken by the Cassini space probe, have allowed scientists to begin to see upper level clouds forming over the North Pole of Saturn. As these clouds start to form, they appear to have their own hexagonal pattern. It's now thought that the hexagon isn't something embedded in the atmosphere, but rather it's something that rises up high above the normal top of Saturn's atmosphere. So here we're looking at a high-level cloud effect where as we look down inside of it, we can see storms at lower levels. This is just one of those things that you look at and it's kind of amazing to observe. Astronomers have been able to watch as the hexagon occurs at stratospheric levels, starting from 2013 when there was almost nothing to October 2014, the hexagon begins to take on shape, and by August 2017 it was fully formed at upper levels. So this is kind of cool. While the hexagon appears to be a permanent feature, it's the upper level clouds that change over time. Over time, with all the observations we've taken of Cassini across decades and large chunks of its full 30-year orbit, hopefully we'll be able to develop weather models to explain this unusual world. Now, those are the stories that I have to bring you today. If you have any questions, I am here to try and answer them. So thank you all for joining us, and I see questions already coming in. So Hannes Vorwerp is asking, how big is the hexagon? I don't have that number right in front of me, but let me go ahead and look it up. Pardon while I type. Okay, so the hexagon itself is about 13,800 kilometers across. This makes it larger in diameter than our own planet Earth. So you could quite easily, with a lot of room to spare, just dunk the planet Earth down inside that hexagon. So I see Larry asking, is this the full disk of Saturn or partial? This is only partial. So what we're looking at goes from 0 or 90 degrees, actually, is a better way to think of it. So this is 90 degrees here at the pole, and then it goes out 20 degrees to about 70 degrees latitude. Looking to see what other questions. So it looks bigger, Paranor, I think because this only goes down to 70 degrees. So we're looking pretty zoomed in on Saturn. Exactly how deep we're able to see into the clouds is something that it's very hard for us to figure out. We don't actually have LiDAR or anything like that, and the true depth down at the eye of the storm has changed with time. But it's just amazing to think that we're essentially looking down through the levels of a gas giant. We do need a polar probe of Saturn. I completely agree. So do we have any other questions out there today? I agree, DPI. We need lots and lots more spacecraft. This is where we really need to see space exploration as something that we do globally, with each nation contributing what it's able, and hopefully more and more nations will join us in our exploration of the solar system in coming years. Thank you for your comment, Paranor. I think that's more a matter of I've only taken a shower. I'm glad to hear you think I look refreshed. Austria was fabulous. I adore the city. I ate far more than I should have, and yeah, life is good. So Hanny, do you mean on the other pole or on the other side? I need more words. I did not, wrong continent, Phoenix. I was in Austria. I will be in Australia in October. Okay, do we have other questions? There's an escaped kangaroo in Austria? Oh man. Oh man. Well, that's a thing. Um, so, a Adam altogether, who I'm determined to read as Adama L together, um, asks, what was the coolest thing at IAU? So there were two things that were really cool. One of them has very little to do with science, and that was Kepler's chocolates. These are high-scale chocolates that are painted to look like the planets. I brought some home and we'll be doing a photo session with them later. And they're super, super tasty. It's a bit embarrassing to admit that the chocolates were one of the highlights, but sometimes a chocolate just needs to take its place as the highlights. Beyond that, this is very much a bureaucratic meeting rather than a cutting edge science kind of meeting. I was super pleased to see that the next meeting is going to be in Australia. There was kind of hilarious wording during the vote that we took. One of the votes was on the coordinate system that describes the rotation of the planet, and it was phrased as, okay, raise your cards to vote in favor of the rotation of the planet. I'm very glad that we all agreed the planet is rotating. The Hubble renaming is a bit of an ongoing thing. So I see Paranor bringing that up. One of the resolutions that we voted on, resolution B4, which is tragically lettered and numbered, is a resolution to rename the scientific expression of how objects at greater distances are accelerating faster away from our Milky Way galaxy once you're looking at things that are not gravitationally bound to our galaxy. Previously, this relationship between distance and rate of escape, for lack of a better term, was termed the Hubble law. We're now looking to rename it the Hubble-Lemaitre law. The justification given for the ordering of the names is it's easier to say, which I think sat wrong with a bunch of us. And the reason for the name change is because Lemaitre was the first to put down mathematically a description of the expanding universe and to tie it to an expanding universe. Other people who had done similar math came to the conclusion that yes, things are moving away, but no, let's add in a constant and call this a steady state university, the universe. This is the de Sitter model. Now, even Einstein is guilty of adding in that cosmological constant that stayed the expansion of the universe. Once you remove that cosmological constant, it becomes possible to see our universe for what it is, an expanding space-time. Now, since Lemaitre was the first to mathematically describe this, and Hubble was the person to observationally describe this, it becomes difficult to figure out which one should have their name go first. If there was a Nobel Prize to be given, they both probably would have received the Nobel Prize, but it's unclear because often theorists are left out. Penzias and Wilson getting the Nobel Prize for the cosmic microwave background, but Peebles not getting it is just one of many examples of leaving out the theorists. So we voted. It was considered a temporary vote because only the people who were in the room, which was far fewer in number than the total number of people in the IAU, were available to vote. We didn't get on the fly the totals of how many people voted for what. It looked roughly like it was 10% abstaining, maybe 20 to 30% voting no, but the vast majority voting yes. Now, they are going to be doing electronic voting, and it's the electronic voting of all members of the union that will have the true weight to say whether or not we should rename this. So I see Phoenix asking, when you say not gravitationally bound, does that mean it needs to be outside the Virgo supercluster? So more like outside the local group. We can see the effects of cosmic expansion between us and the Virgo cluster. We're still falling towards the Virgo cluster, but we're falling much slower than we would if there wasn't this universal expansion. So it's outside our local group, the Triangulum, the Andromeda, all the little dwarfs, that we really see this start to take effect. So Adam Altogether writes, can't wait for the Friedman, Lemaitre, Robertson, Walker Space Telescope. There was actually discussion on whether or not we should include all those names, and the decision was no. Just no. But I'm running out of time. I have my every Tuesday CosmoQuest meeting to come, and so I'm going to need to sign off on this. So we will be coming back tomorrow, same time, same place, to bring you more of the daily news here. Thank you, Trekker Kev. We'll be coming back to bring you more news tomorrow, same time, same place. The Daily Space is, as always, part of CosmoQuest. Click on over to cosmoquest.org and help us map out our solar system. Thank you, Fenmil. I'm confused. There's two of you that have very similar names. Thank you, Fenmil, and thank you, Fengrin, earlier for the subscriptions. So thank you. And Fenmil, I think you're my first Twitch baby, which is a little weird to say. So tune in tomorrow. I will be back this evening, if all goes well, to bring you astronomy office hours. That will be at 8 p.m. local, which is 9 p.m. Eastern, which is, doing math in my head, 6 p.m. Pacific, and 11 a.m. tomorrow if you're in Australia. So hopefully I'll see some of you tonight, and if not, I'll see you tomorrow. I'll talk to you all later. Bye-bye.